So, hello everyone.
So hi, welcome back. So this is the, I think, third talk of today? Oh, fourth, I'm sorry. So Jimmy is going to speak about Kubernetes and deploying Postgres on Kubernetes. He works for SolarWinds, and enjoy. Thank you.
Thank you. I work for SolarWinds. My name is Jimmy. I work in lovely Edinburgh, a very EU-friendly Edinburgh, may I say. And I'm going to talk about how you can get your favorite database deployed on Kubernetes. Now, that sounds simple, right? It's Kubernetes does containers. First of all, how many people here are familiar with Kubernetes? Okay, and who uses it on a daily basis? Fewer. Okay, so the first part of this talk is going to be talking about Kubernetes. So a few of you will be bored because it's things you will already know, but I'm also, the reason I want to do this talk here is to expose the Kubernetes, let's say, workflow and system to DBAs and people who play with databases and see how it can make their lives easier, if at all. So, what's the motivation for this talk? The motivation is, please. Okay. Service-oriented architecture and whatever that encompasses. So everything is moving towards this direction, and Kubernetes is no exception. SOA, including microservices, is the way forward because it decouples your applications from your database, it decouples components of your system from one another. It's easier to code in parallel. It's easier to replace systems when they're decoupled. And that's what SOA is all about. And Kubernetes is a perfect example of SOA because everything is abstracted. You abstract services, you abstract controllers, you abstract deployment methods. Everything is disconnected from the actual code and the actual systems that it runs on. And the second reason is Kubernetes is here to stay. It's not a thing like, if you remember Ganeti, which was another doomed Google project, it's not a thing that's just going to get abandoned and only being peddled around by one company. Kubernetes is supported by the Cloud Native Computing Foundation, and that's a lot of companies, a lot of people behind this effort. So it is very well adopted by the community by now. And it isn't going anywhere. And one other reason is so we can have fewer phone calls that wake us up at 4 a.m. Kubernetes automates stuff so that you don't have to look after your systems all day long. You don't have to be over the systems seeing what died. Did the database die? We need to restart the database. Kubernetes does all that for you. Kubernetes is also free, so you can play around at home for free, or you can get commercial support for it. It's very well supported commercially. Red Hat, for instance, supports Kubernetes very well, and you're also able to get commercial support from, you can buy Kubernetes environments from Google or Amazon. And the reason you can do that is because cloud compute and storage is turning into a commodity now. It used to be a luxury when you could offload the running of your systems to something else, but now it's sometimes cheaper than actually running on bare metal. So it's becoming a commodity, and why not have your systems orchestrated by you, but running elsewhere? Another reason is Postgres is hard. Well, at least industrial strength Postgres is hard. It's hard because you need to think about reliability, you need to think about availability, you need to think about resilience. When a cluster goes down, which system replaces it, which one's the master, which one's the slave, is it replicated, is it backed up? These are things you can all automate using Kubernetes. And the end goal is you want Postgres to be a commodity for your users. If you're a DBA or someone who looks after the database in your environment or your organization, you want Postgres to be a commodity. You want people to just request a database, get it, and then they should forget about you. It should just work. They shouldn't bother you anymore. And that's the end goal. If it's a commodity, then you give it to them, it keeps working, no administration is necessary for as long as it works. And by no means is this presentation an exhaustive list of the ways to deploy Postgres on Kubernetes, or even a good list. It's a few things that I tried out at work and at home, and it's more an attempt to demystify Kubernetes, this magical word for us database people. So this presentation is not me fiddling around with terminals. If you've been to other Kubernetes presentations, you'll have noticed that people like to type into their terminal and move terminals around and show you how it works. So I won't do that. I won't type in the commands just to show how they're typed in, and then press enter, and now it works perfectly, and you see what it does when it works. But sometimes it doesn't, so let me delete the configuration that I left when I tried it at home before the demo and restart. So this presentation is not that, but it is going to talk about the basics of Kubernetes, deploying at small scale, deploying using Helm charts. We're going to talk about that, what it is and how it works. Deploying using the crunchy data Postgres operator. And some observations on the previous methods and in general. So let's start with the basics. So what is a container? So if you're not familiar with the K8S thing, it stands for Kubernetes. It's just a short way to write it. It doesn't hold any meaning. So what's a container? A container is a lightweight, standalone, executable package. It's all in one. It's like a mini system that you deploy. It has all the bits and bobs that it needs to work. It has all the libraries in it. It has all your code. It has the executables. And it's the same everywhere. No matter where you try to run the container, it should behave exactly the same. So this is obviously resource efficient because we used to slice new VMs for everything we wanted to try. So maybe I should try Postgres 11. Let's build a new VM. Now let's change this thing in the configuration, another VM. You eventually run out of resources, whereas containers let you utilize the same resources, whether it's something provided on the cloud or bare metal. And it's also platform independent. It solves the problem of the developer going, it worked on my machine, but why doesn't it work on the server? It's exactly the same. If it works on your machine, it should work on the server. So Kubernetes is a container orchestrator written in Go. supported by the Cloud Native Computing Foundation, as we said. The things it does automatically is scaling, load balancing, and letting you update your application in a safe and controlled manner. So how it does that is it has the Kubernetes API. Everything is controlled through the API. And the API is totally an abstraction. It can be running on bare metal. It can be running on some cloud provider. It can be running on your laptop. It doesn't really care. It behaves exactly the same. And the API exposes what are called resources, because we don't have objects in Go. They've called them resources, and they're the things, the building blocks that make up the Kubernetes API. Also, another thing to consider is the pets versus cattle debate, which means that do you treat your containers as pets that you lovingly take care of, and you would really feel bad if one of them died, or is it cattle that you just breed and they're replaceable? So we're trying to move from a world where we took desperate care of our system and tried not to let the database fail, or it should be up 24/7. What happens if it goes down? We need to not care about that because we know it will go down. So in this case, we treat it as cattle. We have many database replicas. When one of them dies, Kubernetes replaces it with something else. It restarts the service. If you request Kubernetes to run 3 replicas, if one of them dies, it restarts and it moves from 2 to 3 replicas again, and so on. So let's look at a few terms. The cluster in Kubernetes is made up of a master node, which is the thing that runs the API server, which is our interface to the whole of Kubernetes, and some worker nodes. So worker nodes run kubelet in them, and kubelet is the thing that monitors what are called pods. And pods are the basic units of, let's say, equivalent but not exactly containers that run in your system. Namespaces are a way to separate your cluster into many virtual clusters, so you can hand them out to separate users and you can assign resource quotas. So you can have a namespace called database, you can have a namespace called SSO in the same cluster that lets people log in, you can have a namespace called web, where all the web service pods are running, and so on. And you can assign different quotas on CPU or disk usage or memory usage for each one of these virtual clusters. Kubelet, as we said, talks to the master node, and pod is a container or group of containers sharing the same execution environment. What does that mean? It means that effectively they think they're running inside the same box, whatever that box happens to be. And why would you want that? You would want, for example, the containers to share a common volume for storage, or you want them to have inter-process communication. So, more terms. Minikube is a way to run a small-scale Kubernetes environment on, say, your laptop or wherever you want. It's Kubernetes in a VM. So you just install VirtualBox or your favorite virtualization tool, and you just point Minikube in its direction, creates a Kubernetes cluster, and you're good to go. You can start experimenting. Prometheus is the monitoring solution that most people use with Kubernetes. It's described as the best fit for Kubernetes because it's also originated by the Cloud Native Computing Foundation. It has its limitations that people are trying to work around, but let's not get into that now. One other thing I want to mention are custom resource definitions. CRDs are the things you use to expand the Kubernetes API. They're the custom code you write to do the things that Kubernetes doesn't do out of the box and to automate your stuff. So one thing you can write with CRDs is custom domain controllers that are called operators. So if you want something to look after your database, you write a database operator that specifically does a few things that you want. You code it in Go to manage your system the way you want it. If Kubernetes doesn't do what you need to do out of the box, and it manages this application for you. So this eliminates the need for out-of-band automation. You don't need extra sidecars to load on your containers to take care of things, or you don't need hypervisors that keep track of your pods externally from Kubernetes. You can do it all inside Kubernetes, and you can script it and go. Now, Kubernetes is all about defining stuff, and the definitions are all in YAML. Tons of YAML. So if you're involved with Kubernetes, you should expect to be seeing a lot of YAML. And what you put in these YAML files, which I'm not going to show many of them, is you specify the kind of resource. Each resource that you put into Kubernetes has a YAML file that it's sourced from, and you describe the kind. So you start by saying, this is of kind pod, and then you put in some metadata. You say, this is the name of this resource. It's labeled as fast disk or whatever you want to label it with to group things together using labels. And what you put inside is the spec. So the spec in the definition is the desired state for your resource. It's something which Kubernetes should do for you. So if you want the state to be 3 replicas, for instance, you put in the spec. You say spec 3 replicas. Kubernetes will try to have 3 replicas running at all times for you. kubectl, or kubectl as many people say, is the command line tool that you use for communicating with the API. And the thing you do is you feed the YAML file to kubectl create, and it creates it inside your cluster. So immediately you go from source, from a textual description of what you want, to an actual resource created in Kubernetes. And you can use it to run commands like get pods, which will show your pods. Now, one of the basic blocks in Kubernetes is the service. The service is some resource that you define that exposes your pods through a URL. So if you have a group of pods that you want to operate as a database and their replicas, you put them in a service, and the entry point for those pods is the service. It targets the pods to be exposed through labels, and what you put in the definition of the service is a selector that says, I want this one to be the primary, so it selects the primary and exposes that. Types of services are a cluster IP, something which answers on behalf of all your databases. It's a node port, which is, it exposes the same port on each Kubernetes node for this service across all nodes. Load balancer, which uses an external load balancer to send traffic to your services, and external name, which also takes care of DNS. So it's a way to route traffic from outside the cluster into your service. Deployments are controllers. Controllers are a type of resource in Kubernetes that takes care of your systems. And a deployment is basically the controller that automates the running of your application. It can enable you to perform upgrades by sending a command to the deployment. It enables you to roll back to a previous state or a previous version of your application. It defines the number of replicated pods. You can say that please deploy a replica set of these 3 exact replicas for me. And it also has upgrade strategies like rolling update, which means we turn off one pod at a time, replace it with the new version, then we move to the next pod, and so on. Or recreate when we want to take down the entire service and start building new pods from the beginning. Now, let's talk a bit about state. Deployment is mainly useful for stateless applications. So it doesn't matter which box your service connects to. It's really about all of them being identical. So it doesn't matter, you don't have any locally stored differences in each pod. Each one of them can die and be replaced by another one, no consequences. That's basically what stateless means here. But stateful is much closer to our use case when we're talking about databases, because we need persistent storage. We need something that can die and can come back up with the original data it had in it. Because what's the point? And also we need to differentiate between nodes, because you have different data in your master and different data in your slave or replica. So you need some way to have stable tracking of your storage. You need to have stable network identifiers for these pods. You need to deploy them in the correct order, because what if the node doesn't know if it's a slave, if it's a replica, or if it's the master? So you need to take care of all that. And stateful set is essentially what does this for you. Stateful set defines a set of replicas in pods, defines what are called persistent volumes, and what's called a headless service, which takes care of your network and DNS for you. And also contains persistent volume claims. So a persistent volume is storage you define, which is available for usage, and a persistent volume claim is something which is using that resource. So it's the same as CPU. If you have a CPU, pods are using that CPU and memory. If you have storage, then persistent volume claims are what are the pods, let's say, in a way, that are using up your resources of storage. If you delete a stateful set, it has some side effects. It does not remove the persistent volumes. So if you take down the service, it doesn't delete the data, which is kind of safer. And it also doesn't guarantee that the pods mentioned in the stateful set will gracefully terminate. So the thing you should do is scale the replica set, scale the stateful set to a number of 0 pods, and that's how you delete it. So let's look at deploying Postgres in small scale in Kubernetes. The first thing you need is an image, so you can build your own image, or you can use an existing image. The official image is the Docker community quotes official image that is maintained in Docker library. It's what you get when you perform a Docker pull Postgres. This is the most basic image you can pull. Then there's the Bitnami Docker image, which has a few interesting twists. For example, it doesn't have root access to the controller, to the container, sorry. And Crunchy Data also provides containers. There are many different container images you can find. If you search for them on GitHub, it will be really easy to find. So how do you deploy this now? What you do is you create a configuration map for the configuration values. Config map is like a fake volume that you can mount onto your pods, and it only contains configuration. So it looks like this. It's not very interesting. You just describe the kind, the metadata labels, and then some data that you need, like I want my containers to grab these values, like database user password. The next step is you need, as we said, some storage. So you need to create a persistent volume, and you need to create a persistent volume claim for your database that will use these resources. Then you create a deployment that describes how you use this container image and this persistent volume. And then you create a service to expose it. The simplest use case is you write a service of type node port, and that just opens a port on the node which is running Kubernetes. Once you've done that, and I'm not going to go into the YAML of it because you can search for it, it's really easy, it's very well documented. Kubernetes has good documentation on how to write these things, and there are millions of examples on GitHub. The last thing to do is connect to your database, and you can do that through the exposed port on the node, or you can use kubectl to do port forwarding and connect on localhost. Another method is Helm charts. What is Helm? Helm is a package manager essentially for Kubernetes. Helm is the client that you run the commands with, the same as you would do with yum or apt-get. So you run the commands to install and remove through Helm. Tiller is the server-side component, because you need something to receive these commands from within the Kubernetes cluster, and you have to have Tiller running to respond. And charts are the descriptions of these packages. And you guessed it, it's also YAML, and they describe a set of related resources, so you can group everything that we mentioned, like persistent volumes, services, deployments, definitions into one chart, and that will create all of them at once, thereby giving you an application package that you can use in Kubernetes. And you can also customize this prior to deployment. You have a file called values YAML, which is getting read by Helm as it's creating your deployment. And you can also add additional files to your chart that get loaded into your containers as they're being deployed on Kubernetes. Our use case for Helm, for Postgres, is that it's a one-step stop installation of a database. And also you can request replicas for this database. So in one command, using Helm install this, it makes sense to be able to deploy with only one command without configuring anything. The chart that I'm going to go into is contributed by Bitnami, and it uses their own image repo, but you can substitute any image you want and it will still deploy it. The installation is dead simple. It says Helm install, give it a name, and give it you can optionally give it some values like configuration for your Postgres instance, which is all documented here. And you then specify the name of the package. And you want stable Postgres, and install stable Postgres. Release in this context means the name of your deployment. So my database, or I don't know, sales database, or whatever you want to name it. It doesn't have anything to do with release numbers. And the output of this command will be some magic that you can run to connect to your newly installed instance. And as we said, you can already provide files that will be fed into the installation. So you can provide your own PostgreSQL conf or PGHBA conf. You just put them in the files folder, because charts are a collection of files in a folder, and if you put them in files, they will be mounted as a config map and will be used by the pods that you will deploy. And this is the output. When you run it, it says, I created these resources for you, these services, this is the IP that they got. It is a stateful set, and right now the default configuration is it only creates one pod to connect to. And at the time of the output, you can see that it wasn't ready yet, because Kubernetes does eventual consistency. You describe the state that you want. It doesn't guarantee that it will get there in milliseconds or instantly or block until you get a response. It takes care of things for you and is eventually consistent. It brings it to the desired state. So it gives you some magic. It says that this is how you'll access your instance from within the cluster, and this is the way you get the password. This is how you can connect to your database from port forwarding or through the cluster. Now, the internals of Helm charts, of this particular Helm chart, is it creates, as we said, a stateful set with only one replica, so you have one database. It creates a headless service and a persistent volume claim to claim storage from your storage provider. You can load, you can configure this Helm chart to load your own custom scripts, the things that you always did when you installed a fresh Postgres instance. You can just put them in the files folder and they will get executed for you as the instance comes up. It can also start a metrics exporter to Prometheus. And this project here, the Postgres exporter on GitHub, has a few definitions of exported metrics. So if you install this on your pod, then it will send these to the Prometheus instance in your cluster, and you'll be able to get performance metrics and other things from your pod. For example, it can output pgstat activity, replication, or even custom queries that you use, that you write yourself to determine how your pod or your database is doing. Another chart which I found interesting is the ready-made Patroni chart. You can use it directly from the Helm incubator, which is like the staging area, let's say, for Helm charts. It also creates stateful sets of a master database with replicas. The default installation in this case is 5 nodes, and it uses Spilo, which is the combination of Postgres and Patroni, and they're put in the same image by Zalando. The way you install it is you add the repository to Helm, and you say, please get it from here. You update the dependencies, and then again, Helm install this thing, incubator Patroni. And similarly, it creates the same type of cluster. Now, let's look at something completely different, which is the operator pattern. The operator pattern is you have some Go code running your database, administering your database for you. So instead of fire and forget, in the case of Helm, which is a package manager, you run the command, it installs it, you forget about it, and the native Kubernetes controllers like deployment and stateful set take care of the running for you. In this case, you can do more advanced stuff because the crunchy operator knows about databases and it knows about Postgres. And you can find it here. It's also open source on GitHub. You can deploy Postgres with, again, streaming replication. You can also send it commands to scale your databases up or down. You can add additional features like PG pool and PG bouncer on your deployments. You can add metrics, as we saw with Helm chart. You can use the operator to change policies in your cluster. You can use the operator to assign labels to your pods, to your databases. You can also perform minor version upgrades, backups and restores. And it also has a task scheduler, so you can schedule backups and they will be performed automatically. And everything within the Kubernetes cluster. You don't need to have anything external. You don't need to have a backup machine that runs a cron job that does this. This is all done internally. So what you do is you git clone the repo, you check out whatever version you want. The latest one is a bit risky, but some of them are quite stable. You then give it the required environment. For an example deployment, you set up an example namespace called demo, and you can find the configuration of the operator in this YAML file here. The next step is you need to give the operator permissions on the cluster to create the objects that it needs to, the resources that it needs to, and the controllers that it needs to. And then by make deploy operator, it's a convenience method that runs the script that actually deploys it for you. PGO is the client. PGO is the thing that you use to interact with the operator once it's been loaded into your cluster. And it has capabilities like create cluster. In this case, cluster is what we call cluster in Postgres. It's a database instance, a database server that contains database instances. You can give it parameters like metrics so that it can export metrics immediately from creation. If you do a PGO show cluster, it will show you the state of the cluster. It will show you how many nodes it administers. And by scale, it will show you, it can scale it up or down. So you can add replicas or remove them. It can also create PG Bouncer and PG Pool deployments across your nodes, your pods. And it also knows about backrest, which you can use to create backups of your cluster with a single command. Or if you don't use backrest, you can just type in PGO backup, and that will do a PG base backup of your stuff. Restore my cluster does what you expect it to. You can also instruct it to perform manual failovers to see what happens when another pod takes over. And the way you do it is PGO failover my cluster query. That should be 2 dashes, sorry. That gets the failover targets, and then you say, my failover target 1, I want to target that for failover. So, a few observations. On deploying by hand, it's easy. It's good for getting started quickly. You can find templates. It's dead easy to copy the YAML, substitute your own values in the configuration, just fire and forget. It offers decent isolation. It's comparable to the isolation a VM would give you, and it's much less trouble than creating VMs and then creating drives to attach to the VMs, and how do you share drives and so on. It also saves resources because it can reuse the free memory and disk and CPU that is not used in the cluster node, but it also doesn't offer any cloud native advantages. It's convenient, but it's architecturally, it's really about the same as a VM if you don't leverage any of the Kubernetes controllers. Now, for production usage, I think it would be a nightmare to have everything deployed by hand, because in order to find out what's happening, you would have to dig through all these YAML files, and then you would have to examine your cluster's resources and query everything in order to find out what's happening with it. So it's not ideal. And it also, the point behind Kubernetes is to avoid having an army of DevOps or DBAs looking after your stuff 24/7. So it kind of defeats the purpose. Helm charts, good for one-time deployments. Like, I don't care. I need to deploy this database and forget about it. I can scale it up at will. I can add memory. I can add disk to it. I don't really have any requirements. So it's good to fire and forget. It's very clean and transparent because everything is defined in the YAML file. You find the chart, you read it, you see exactly what it's deploying and exactly what objects it's creating in your cluster. One sticking point is how do you do major version upgrades? There is no way to automate that through the Helm chart. You can perform minor upgrades by substituting the image, but when there's binary incompatibility, like in a major version change, what do? You need to handle that manually. Slave replicas don't actually do failover automatically unless you explicitly set it up to work that way. So out of the box, you won't have an HA cluster, in a sense. But it does give you, because it's so simple, it gives you the flexibility to carry on using your existing solutions. It's just that the stuff will be running elsewhere. It will be running as containers inside Kubernetes cluster as opposed to VMs or on bare metal. An advantage is that it can be used without really special permissions. If you have permissions within a namespace to create resources, then you can just install Tiller, you can run Helm, and you can deploy anything. The crunchy operator, on the other hand, is, let's say, less transparent because unless you go into the Go code of the controller, you don't know exactly what it's doing. But it does let you perform many actions through the CLI, and it also takes care of a lot of stuff automatically. A disadvantage is that you need to be cluster admin in order to use it right now. You need to create the role-based access control rules, and you need cluster admin permissions to do that. And because CRDs, custom resource definitions, as we said, the ways you extend the Kubernetes API, are not namespaced. They're universal for the whole cluster. So you can't say, I'm deploying this in namespace sales. You need to have your cluster admin create it for you, which in a multi-tenant system, if you have like hundreds or thousands of tenants, can get tedious for the administrator of the cluster. And this is the relevant thing. They were asking for this functionality on GitHub, but the developer said, we're not going to look into namespacing custom resource definitions for the time being. Also, crunchy operator is really nifty, but I cannot either say use it in development, go ahead, it's fine, or say don't use it in development. It's your own risk because it's under heavy development. It may not be ready for production, or it may do 100% of what you need. You need to try it out on your own and test it to make sure that it's exactly what you want to get. A caveat is that Kubernetes is also under heavy development. It changes from minor version to minor version with breaking changes. Everything changes all the time. Observations continued. A hard problem that is not solved by the things that we mentioned is how do you create a Postgres cluster that has multiple write nodes? It's not easily solvable right now in Kubernetes. Multi-master is not always the solution. Do you really want one database where people from all over the place write with different latencies and you need to take care of locking for everyone? Is that something you really want to deal with, just to have people writing into the same table or set of tables? But what you can do is use the solutions that we mentioned with PG Logical and expose another way to replicate tables and write into remote tables. And you don't even need a custom image for that. For example, you can add it as a post-install hook in Helm, and it will just run it for you in your container as soon as it creates the pod. So you can just have a command that says apt-get install PG logical, create extension so-and-so, and you can start using it. Now, what alternatives do we have? You can go for database as a service or a whole platform as a service, like Heroku, which costs a lot more than what we mentioned. You can also go the way of managed databases on the cloud, like Enterprises DB Postgres, that it runs on AWS and manages for you. And then there are these solutions here that you can use that offer more or less Postgres in some sort of guise or something which is compatible with Postgres. Your mileage may vary. It is what it is. It is a commodity. It's really cheap compared to other managed systems, but you get what you pay for. You can define all of the above as a service in Kubernetes and connect them to endpoints. So Kubernetes can even administer things that are running, can even orchestrate things that are running outside it. All you need to do is define an endpoint, and you can say that this endpoint, this IP that Heroku gave me is a database, and it's part of this cluster. So, thank you very much. Any questions?
Can I have questions? Yeah, so the first question, hard one. Why you didn't mention the Zalando operator, which is better on Patroni?
I didn't have time to look into it. There is also a Zalando operator that I haven't had the chance to try it yet. So,
okay, another interesting question. Is it any proxying level in operator, in cringe data operator, proxy for queries which can handle some ingress point which can handle failover of node?
I'm not aware of that. I haven't really tried it.
Okay, another question. Can I use local storage instead of PVC? I mean, host
Yes, of course. Storage is totally independent. You can use any sort of storage as long as you define it in Kubernetes as...
without storage class, I mean empty dir, for example, or host path.
You can use host path, yeah.
I can use host
yes.
part. Another question, what kind of replication can I use?
Excuse me, probably some other people are going to ask questions.
Okay, last question about... Okay, the last. About backups. It is good to have backups, database and backups in Kubernetes. Can I make backup to S3 compatible storage?
Yes, you can define it to go into any sort of storage that you have attached to Kubernetes. Because your storage is an abstraction in Kubernetes. It can be an S3 bucket, it can be a volume somewhere else, it can be EBS, it can be whatever you want.
Speaking of storage, so persistent storage is mostly networking, I suppose. So is it more susceptible to the fsync bug?
Sorry?
The persistent storage is
Yes.
usually network storage, I believe. And so is it more susceptible to fsync bug? Or?
It depends where your cluster is running. If you've defined it to use network storage that is somewhere else, yes. If you defined your node to use local storage that is attached to the node, then it's local. It doesn't have to be over the network, is what I'm saying.
Any questions? Any questions from anyone else? Okay. Just one question, please, because we have just one minute.
You have integration with Prometheus, but what about query analytics? Can I monitor what is going in my cluster? Is anything in operator with monitoring with query analytics?
Well, they mostly tend to go the way of Prometheus. But you can change the Go code and you can make it output to whatever